Something is happening to this planet, not slowly, not quietly, not in ways that can be ignored anymore. Earth is changing in real time, and the signals are everywhere. Glaciers that took 10,000 years to form are vanishing within decades. Ocean temperatures are breaking records that scientists did not think were possible yet. Storms are intensifying faster than models predicted. Wildfires are burning in places that were never supposed to burn. This is not a distant warning. This is the present. And the story of how we got here is one of the most complex, urgent, and genuinely fascinating mysteries in the history of science. If you want to understand what is actually happening to this planet, subscribe now, because this is only the beginning of the story. To understand what is changing, you first have to understand what Earth actually is. Not just a rock floating in space, but a living, breathing, interconnected system. The atmosphere wraps around the surface like a thin shell of gas, just 100 kilometers thick, barely a fraction of the planet's total size. Within that shell, energy from the sun enters, bounces around, warms the surface, and radiates back outward. The balance between incoming solar energy and outgoing heat is what determines the temperature of the planet. For billions of years, that balance has shifted, sometimes dramatically. Earth has been a snowball, completely frozen from pole to equator. It has been a hothouse, with no ice anywhere on the surface. These were not catastrophes caused by human activity. They were the natural rhythms of a planet responding to changes in its orbit, its volcanic activity, its ocean currents, and the composition of its atmosphere. The sun itself plays a central role. Variations in solar output, shifts in Earth's axial tilt, and changes in the shape of its orbit around the sun have all driven massive climate shifts over hundreds of thousands of years. Scientists call these Milankovitch cycles, and they explain the ice ages that have come and gone across deep time. Here is where the mystery deepens. When scientists look at the geological record, they can trace past climate changes through ice cores drilled from Antarctica and Greenland. Trapped inside those ancient layers of ice are tiny bubbles of air from hundreds of thousands of years ago. Those bubbles tell us exactly what the atmosphere looked like long before humans existed. And what they show is striking. Carbon dioxide levels and temperature have moved together across ice ages and warm periods in a clear, rhythmic pattern. But something about the current moment does not fit that pattern. The rate of change happening right now is happening faster than almost anything seen in the geological record outside of mass extinction events. Carbon dioxide concentrations in the atmosphere have risen from approximately 280 parts per million before industrialization to over 420 parts per million today. That is a jump of more than 50% in roughly 200 years. In geological terms, 200 years is not even a blink. It is a fraction of a second on the time scale of Earth's history. Scientists did not expect this pace. Even the most concerned researchers in the early 20th century did not anticipate how quickly the system would respond. What makes this story even more complex is that warming does not mean everything gets uniformly hotter everywhere at once. The system is far more complicated than that. Some regions are actually experiencing unusual cold snaps, not because the planet is cooling, but because warming is disrupting the jet stream, the high-altitude river of wind that normally keeps cold Arctic air contained near the poles. When that boundary weakens, cold air spills southward in unpredictable bursts. Meanwhile, the Arctic itself is warming at nearly 4 times the global average rate. The oceans are absorbing more than 90% of the excess heat trapped by greenhouse gases, and they are also absorbing enormous amounts of carbon dioxide, which is changing their chemistry in ways that affect marine ecosystems from the smallest plankton to the largest coral reefs. Deep ocean circulation patterns, which act like a global conveyor belt moving heat and nutrients around the planet, are showing signs of slowing. Scientists did not expect this to happen so soon. The Atlantic meridional overturning circulation, one of the most important of these systems, has weakened to levels not seen in over 1,000 years. If it slows significantly, it could dramatically alter weather patterns across Europe and North America in ways that are difficult to fully predict. The numbers themselves tell a story that is hard to look away from. Global average surface temperatures have risen by approximately 1.2 degrees Celsius above pre-industrial levels. That might sound small, but consider this. The difference in average global temperature between the peak of the last ice age, when massive ice sheets covered much of North America and Europe, and today was only about 5 to 6 degrees Celsius. 1.2 degrees of warming across the entire planet represents an enormous amount of additional energy in the climate system. Sea levels have risen by roughly 20 centimeters over the past century, and the rate of rise is accelerating. The 10 hottest years on record have all occurred since 2010. Extreme weather events, from heat waves to heavy rainfall to powerful hurricanes, are becoming more frequent and more intense in ways that align with what physics predicts when you add more energy to a complex atmospheric system. Scientists use complex climate models to project what might happen over the next 50 to 100 or more years, and those projections carry a range of possibilities depending on how much greenhouse gas humanity continues to release. Under higher emission scenarios, average temperatures could rise by 3 to 5 degrees Celsius or more by the end of this century. Under lower emission scenarios, that rise could be limited to closer to 1.5 to 2 degrees. The difference between those outcomes is not just a number. It is the difference between a challenging but manageable future and one involving widespread disruption to food systems, water availability, coastal cities, and ecosystems that billions of people depend on. But the models also carry uncertainty. There are feedback loops in the climate system that are not fully understood. Permafrost thawing in Siberia could release vast stores of methane. Cloud behavior at large scales remains difficult to model precisely. Scientists are honest about what they do not yet know. And that is perhaps the most important thing to hold on to as this story continues to unfold. This is not a closed case. It is an active investigation into the behavior of the most complex system human beings have ever tried to understand. Earth has survived far worse than what it is experiencing now. The planet will endure. The real question is what kind of planet it will be, and how quickly it will change, and whether the systems that support the particular version of life that exists today can adapt fast enough to keep pace. The data is real, the changes are measurable, the science is ongoing, and the next chapter of this story has not been written yet. Thanks for watching. If you want to stay ahead of what's happening to Earth and beyond, don't forget to subscribe to be part of our epic journey. If you're ready to go deeper, check out my latest video here now.